Good afternoon, everyone. Welcome to our online session. Now, today I want us to discuss chapter 2, which is your semiconductor device, of which I've already started with the rest of the group. Just want to do the repetition of this so that we can have a thorough understanding of exactly how to do or how to work with a semiconductor device. Now, the semiconductor device that we are going to work with, it is a semiconductor device of a diode. Now, the first thing that we need to understand is what is a diode. Now, you will see that based on the explanation of a diode, it is a device that allows current to flow in one direction. It allows current to flow in one direction. So which means this device consists of polarity, which means you will have a positive side, and then again you will have a negative side. You will have a positive side, and then again you will have a negative side. Then you will have a schematic symbol, which is an electrical circuit representation of this device, of which this schematic diagram of this device, it is indicated or symbolized in this manner, whereby you will have a cathode, an anode, and you will have a cathode. Now, with the anode, it is the positive side of the device, and then the cathode, it is the negative side of the device. The anode, it is the positive side of the device, and the cathode, it is the negative side of the device. Now, the structural construction of this device in terms of electrical circuit, it consists of two doped regions. It consists of two doped region. It consists of the P region, whereby on the P region, you will find majority of holes and minority of electrons. On the P region, you will find majority of holes and minority of electrons. Then the next dope region, it is your N region, of which on the N region, you will find majority of electrons and minority of holes. You will find majority of electrons and minority of holes. Now, in between the two regions, it is separated by what we call a depletion region. It is separated by what we call a depletion region. Now, with the depletion region, it simply means that the content that you find on the P region cannot automatically escape to the N region, or the content that you find on the N region cannot automatically escape to the P region, which means it leaves a barrier between the two regions. It leaves a barrier between the two regions. Now, the function of this device, it is when an electrical circuit, or it is when you have got current flowing within this device here. So now if I take this device and connect an electrical circuit within this device so that we can see how this device will function within your current flow. Then we're going to say, let's connect a conducting wire on the P region. Let's connect an electrical conducting wire within the N region. But now, when we connect these, we must make sure that the energizer with respect to your current flow, the positive side of the energizer is connected to the P region, and the negative side of the energizer is connected to the N region. The positive side on the P region, the negative side on the N region. But now here, we are connecting these with respect to the structural device. So which means when we look at how the schematic symbol is, when we look at how the schematic symbol is, you will see that this structural representation of the diode, schematically, yes?
You can continue.
Okay. When we look at this schematically, then you will see that with respect to how the symbol is used, then the P region will be your anode and the N region will be your cathode, which means you will have the P region, which is your anode, and you will have the N region, which is your cathode. So which means in terms of schematical symbol of an electrical circuit connection, this is how your diode it is going to be connected. But now, once you connect these, then we're going to say which type of current are we working with. You will see that the type of current that we are working with, we work with a conventional current. So which means we have current which is flowing from the positive side of your source through the conducting wire with your R limiter, then into the P region, which means from the positive side, we are going to feed more of the positives into your P region. We are going to feed more of the positives into your P region. Now you will see that already there are more of the positives that are existing into the P region. You have got more of the positives that are existing within the P region. Now you'll see that the more you feed in the positives, the ones which are already there, they will start feeling uncomfortable. So which means now they need to push your depletion region from being widened to being narrow, so that it can jump from the P region into the N region. Now, when the holes jump from the P region into the N region, which means they're going to combine with the electrons, which are the majority on the N region. Now, with the jumping of these holes, now you will see that you're going to create a barrier potential. You're going to create a barrier potential, of which that barrier potential, it becomes a booster with respect to your holes jumping from each region to the next region there. But now, within the conducting of this component, that barrier potential, it is measured, of which based on the material which is used, then it can determine what is your barrier potential voltage. Now we have got two types of materials which are used to construct this device here. We have got the silicon material and we have got the germanium material. We have got the silicon material and we have got the germanium material. Now, if it is of a silicon material, you will see that the barrier potential which is created when these combinations starting to exist, then you will have a barrier potential of 0.7 volts. A barrier potential of 0.7 volts. But if it is a germanium material, then it will have a barrier potential of 0.3 volts. Now, when these two voltages, depending on the material which is used, it is being established during the movement of these holes with the combination with the electron, then we can say that this device, it is on a conducting mode. But now we can see the conducting mode of this device based on the type of the device that we are working with. Now we have got three types of devices. Also, we have got three types of working mode of this device. We have got an ideal type, we have got a practical type, and we have got a complete type. We have got an ideal type, We have got a practical type and we have got a complete type. Now, with the practical type, you will see that when you look at this device, you are looking at this device during the function as a normal switch, during the functioning as a normal switch, whereby if current it is allowed to flow within this device. If it is current, it is allowed to flow within this device, which means that is, or you will have a closed switch. But now that it is when you are working with this device as an ideal mode. Then again, the next mode, it is when you have got this device as a practical mode, whereby it is an internal an internal voltage and a switch, and an internal voltage and a switch. And an internal voltage and a switch. Now, you will see that with the practical mode, that is where now we can be able to go and measure these two barrier potential. With the practical mode, that is where we can go and measure these two barrier potential. But now with the barrier potential, which is your internal resistor, based on the movement of your holes from its region to the next region, or jumping from its region to the next region, so that it can combine with the minority that it finds there. Then you will see that with that barrier potential, which is your internal voltage, it is your 0.7 volts or your 0.3 volts. But now, if that voltage it is established, which means you have got your switch, which is closed there, whereby it allows the current to flow. You have got a switch which is closed, whereby it allows the current to flow. Then the next mode, it will be your complete mode, whereby you will have a barrier, an internal voltage, then connected with the resistor, then you have got a switch. You have got a switch, of which with this internal resistor, which means again the barrier potential based on allowing the current to flow. Remember, all of these, it is happening with respect to the device allowing the current to flow. If the current cannot flow, or if the current is not flowing, which means your switch will always remain open. Your switch will always remain open. And if your switch always remain open, which means you cannot measure the barrier potential. You cannot measure the barrier potential, which means there will be no movement of holes or your positives from the P region into the N region. Now you will see that this, it is explained more thoroughly when we look at how is the application of this device within an electrical circuit. Now this is just a basic fundamental with respect to how the diode functions on an electrical circuit. Anne, can you screenshot this?
Yes, just give me a moment. You can continue.
Okay. Now, if I look at this within your practical application of this diode, if I look at this within your practical application of this diode, now you will see that whatever that happens, you will have a circuit connection that will consist of a resistor, which is your R limiter. Then you will have your diode. Then you will have the voltage connected there. Now, as an electrical circuit, now we want to see how is the response of this component based on the theoretical analysis of a diode. Now you will see that according to the description of this component, it says for this component to be able to function, it needs to undergo 2 modes. It needs to undergo 2 modes. Now you will see that those modes, it's either it is of a forward bias mode or it is of a reverse bias mode. It's either it is of a forward bias mode or it is of a reverse bias mode. But now, with this forward bias, reverse bias, now it says it's either it allows current to flow or does not allow current to flow. It's either it allows current to flow or it doesn't allow current to flow. Now, if it allows current to flow, which means here it is a closed switch. If it allows current to flow, which means it is a closed switch. If it doesn't allow current to flow, which means it is an open switch. Now, it simply means that when we work with this device, we are going to work with this device within the 2 conditions. We are going to work with this device within the 2 conditions. It's either it is a closed switch or it is an open switch. It's a closed switch or it is an open switch. But now, with this open and closed switch, it will be based on the amount of voltage that builds within this component here. The amount of voltage that builds within this component here, because you will see that when we do this analysis, we base this device of ours, as a practical mode. We base this device of ours as a practical mode, which means you will have terminal voltage with a switch connected. You will have internal voltage with a switch connected, which means for this switch to close, we need to reach a certain voltage. For this switch to close, we need to reach a certain voltage, of which that voltage will depend on which type of diode are we using. Are we using a silicon diode or are we using a germanium diode? Are we using a silicon diode or are we using a germanium diode? And we know that if we are using silicon 0.7, we are using germanium 0.3 volts. Now, if this voltage it is reached, which means it forces the switch to close. And if the switch closes where this voltage is reached, then your diode turns to a forward bias mode. But now, if this voltage it is not reached, which means this component goes into a reverse bias mode, which means the switch it is open. Now, those are the two states at which you will work within this component here onto an electrical circuit connection. But now, how does it get to a state whereby this voltage or this barrier potential it is established within this component? It is based on what is your input voltage. What is your input voltage? Which means here you must have a variable input voltage with that variable input voltage so that it can gradually increase up until it gets this component from a reverse bias mode into a forward bias mode. Now, for an example, if I say I'm here at 0.1 volts, that is my input voltage. I am at 0.1 volts. Now, if I am at 0.1 volts, which means I am energizing with respect to 0.1 volt. But now, with this 0.1 volt, compared to the switching voltage of this component, you will see that the switching voltage of this component is greater than the voltage which is used to energize the flow of current, which means it doesn't have enough power to get this component into a working mode, which means this component will remain as an open switch up until I adjust this voltage so that the magnitude of the input is equal to or greater than the switching voltage, which means for me to be able to see how this component is going to react within the current flow there, then I will go and say the switching voltage, if it's 0.7, which means I must make sure that my input voltage, it is high enough to energize the flow of current, whereby it will force this component to move from a reverse bias state into a forward bias state. Which means if I say at 2 volts here, I'm energizing at 2 volts here. Compared to these, I'm energizing at 2 volts. Compared to these, I will see that the energizer is greater than the switching. The energizer is greater than the switching. If the energizer is greater than the switching, which means it's going to allow current to flow through. And if it allows current to flow through, which means now this component, based on these, it moves from a reverse bias mode into a forward bias mode. And once that component goes into a forward bias mode, which means now that component, it is functioning properly. So which means if I take a multimeter and put one probe here and one probe there, I am going to measure the voltage. I am going to measure the voltage that exists within this component during the movement of your holes from one region to the next region, of which, based on the material, it is going to be a 0.7 volts, or it is going to be a 0.3 volts. Now, once I measure those two voltages, or once I measure either of these two voltages, then that component is functioning properly. And that function, then it is defined as a forward bias mode. Now, when we continue with this analysis, then I will go and say the application of these, it is an application when your circuit, it is of a circuit limiter. When your circuit, it is of a circuit limiter. Now, with the circuit limiter, the type of source that we are using, it is of an AC source. Remember, when we did circuit analysis, we talked about two types of energizer. We have got a DC energizer and we have got an AC energizer. We have got a DC energizer and we have got an AC energizer. Now, when we look at an AC energizer, within a diode circuit, you input AC. Now, again, you need to be very careful which type of source are you working with. Are you working with the AC source in terms of RMS, in terms of peak, in terms of average, or in terms of peak to peak? Now, when you work with these type of a component, you must make sure that your source, it is of a peak source. Your source is of a peak source. So which means in any state where the source is given, you must make sure that you convert it into a peak voltage. Now, if I connect an AC source into an electrical circuit as an energizer, then I have my R limiter. Then I say that is 10 kilo ohm. Then continuation. Then you have got a diode connected there. Then opposite to this, I said connect a resistor there. Then I say that is your RL, where I do my measurement of the output. Then I say this is my D1 referencing. Then I say this is, for example, 100 kilo ohm resistor. Now, then I say with this component, I am using this as a germanium. I'm using this as a germanium. Then I will say with the germanium component, which means I know that if this component goes into a forward bias mode, if this component goes into a forward bias mode, it simply means that the barrier potential that is going to be established within this component, it is going to be a 0.3 volt. Now, when I say the input, then I say my input is 10 volts peak. My input, it is 10 volts peak. Now, with this type of a circuit, we'll say that is your diode limiter circuit. So that is your diode limiter circuit, or a diode clipper circuit. That is your diode limiter or a diode clipper circuit. Now, if I look at these, I want to see how is this component going to react with respect to this type of source. How is this component is going to react with respect to this type of source? Now you will see that the reaction of this type of circuit, it will be measured within the graphical aspect. It is going to be measured within the graphical aspect. Now, when we look at this, we will look at this as from the input to the output. We look at this from the input to the output. Now, how is your input with respect to this? You will see that with your output, so with your input, moving from 0, gradually increase, which means that is your sinusoidal sine wave. That is your sinusoidal sine wave, whereby with your sinusoidal sine wave, you will have a maximum turning point of 10 volts peak. Then you will have your minimum turning point of minus 10 volts peak, minus 10 volts peak. Now, what does this component do with respect to this input voltage here? What does this component do with respect to this input voltage there? Now you will see that according to electrical circuit analysis, you will have current flowing within the conducting wire, energized, positive, negative, which means you're looking at conventional current. Current will flow through the conducting wire, R limiter, continues flowing. But now when it gets to the junction, what does it see? It sees a junction whereby with the junction, it knows that I'm going to split in that direction and also I'm going to split in that direction there. So it means it's going to split into two directions. But now, according to the analysis of Kirchhoff, with respect to circuit networks, it says the current entering the junction is equal to the sum of the current leaving the junction. Partially, that is a parallel network, but it can only be complete if the current or the sum of the current entering the junction, the sum of the current entering the junction is equal to the current leaving the junction. Where the two statements complement one another, which means is connected there, it is of a parallel network. Are you saying something?
You can continue.
Okay, it is of a parallel network. Now, if I look at this, I will see that how it is splitted, how it is going to recombine, which means it leaves this component and that component to be parallel to each other. Now, if these are parallel to each other, then we know that parallel circuits are current divider circuit, voltage remains the same. If I look at how this is going to work out, then I will say that the current is going to flow into this component. But now, once it continues, what's going to happen, or how this component it is going to react when the current flows? If I look at the magnitude at which it has energized the current compared to what will aspire here within this component, it says with this component, you must reach a voltage of 0.3 volts. You need to reach a voltage of 0.3 volts. Now, if I want to reach a voltage of 0.3 volts, if the energizer or the magnitude of the energizer is greater than the magnitude that switches on this component, which means this component can move from a reverse bias to a forward bias mode. But that is driven by how is the magnitude here. As long as it's greater than the switching on, which means that component is gonna move to a forward bias mode. But now when it moves to a forward bias mode, then we ask ourselves, when do I get to take this component from its state into a forward bias mode? You will see that that is happening during the cycles of your input signal. But now, in which cycle or in which part of the cycle, you will see that it is happening during the positive cycle. It is happening during the positive cycle, which means during the positive cycle, I will get this component to move from its original state into a forward bias mode. So which means when I measure the voltage, your V out, when I measure the V out, I am going to measure the output voltage based on the voltage that has been generated there. And if I look at this very carefully, the voltage that has been generated there is 0.3 volt, which means my V out here during the forward bias is going to also to be 0.3 volts. And if that voltage is 0.3 volts, which means the output signal measured graphically during the point or the initial point with gradually increasing initial point, gradually increasing, it's going to increase switching on up to a certain point, of which at that point, that is where your 0.3 volts is. So which means your voltage will stay at 0.3 up until your signal, it moves positively, maximum peak, then decreases up until this point here, where it stays your output at 0.3 volts. Then the moment it goes below 0.3 volts, which means this component is going to move from a reverse bias, so from a forward bias into a reverse bias mode, which means now your output decreases up until 0. Then it leaves this component back to its state, which means at the output, when I measure during the positive cycle, that is the piece of voltage that I'm going to measure there. Now, with these type of circuits, we know that this circuit, what it does to the input, it eliminates everything that is beyond this voltage here. It eliminates everything that is beyond this voltage here. Now, beyond this voltage, it is a positive 0.3 volts. Anything that is above 0.3 volts must be eliminated, which means from here going upwards at the output, it is not being considered. Therefore, that's why they call it a diode limiter or a diode clipper circuit. But now, with these, you have got 2 cycles. With these, you have got 2 cycles. This is happening during the positive cycle. But now what happens during the negative cycle? Because it needs to have a complete cycle. What happens during the negative cycle? You will see that these will move from a reverse, so from a forward bias into a reverse bias. Now, if it moves to a reverse bias, then this component, it becomes an open switch. This component, it becomes an open switch. Now, if it is an open switch, you will see that it will gradually decrease up until 0. Then this is an open switch. Then continuously with respect to your input, instead of your input or your current with continuously flowing, seeing a junction, because this device, it is at a reverse bias mode, open switch, then your current continuously flowing without being splitted, then it looks at this entire circuit as a series circuit. It looks at this entire circuit as a series circuit. But now, because it is looking at this as a series circuit, then it goes and say, what will be the response of the output if this component here no longer exists? What will be the response of the output if this component no longer exists? Now you will see that the response of this, that is during the reverse bias mode, which means now when you measure your output voltage, your V out will be measured by, according to Kirchhoff, in terms of series circuit. It says series circuit are voltage divider circuit, where the current remains the same. And if series circuit are voltage divider circuit, then I need to go and apply the voltage divider rule, because I know that the sum of voltages across your closed loop circuit with the components must be equal to your supply voltage. Then with the voltage divider rule, I will go and say my 100K, which is my RL, divided by 10K plus 100K multiplied by your input voltage, which is your 10 volts. Now with this voltage, that is the voltage that I'm going to measure within the output. You will see that with the small decrease of the your input, with the small decrease of your input, then you will see that your signal, it is going to be a complete signal with respect to what? With respect to your input signal there. Just a small margin, depending on what is the magnitude of your resistor there. But now, this simply means that during the cycle where this diode has switched off, during the cycle where this diode has switched off, it allows the input to be a replica of the output. It allows the input to be a replica of the output. But that is happening during the reverse bias mode, which means here, what I'm going to find the V out, of which my V out is a V out of 100K divided by 10K plus 100K multiplied by your input voltage there. Now, the replica, it is complemented by this statement here. It is complemented by this statement here, which means what I'm going to find, I am not going to tamper with the negative cycle, because the negative cycle never switched on the diode. The negative cycle never switched on the diode. In an actual fact, the negative cycle switched off the diode. The positive cycle switched on the diode. That's why the positive cycle was tampered with, because we never wanted anything that is above the point of switching on. But we wanted everything that had to do with this diode when it was not on its working condition. That now the type of circuit that we see, in terms of the application, in terms of the application with the limiter or the clipper, then we say this circuit, it is of a positive clipper circuit. Positive clipper circuit simply means that during the positive cycle, we had to clip off what didn't switch on the diode. We had to clip off what didn't switch on the diode, or during the process of switching on what the diode didn't use. We had to remove it, and we are only left with a small portion, which is the switching on of the diode and what switched off the diode. That is your positive clipper circuit. Now, with this positive clipper circuit, again, we can go and say, Ali, can you screenshot this?
Okay. You can continue.
Now, with this positive clipper circuit, we can go and say, now, the voltage that we're measuring at the output, the magnitude, it is too small, 0.3 volts, it is too small. I don't want to use a 0.3 volts DC, because you will see that it becomes a DC voltage. From this point here, it becomes a DC voltage. This one is a DC voltage. It becomes a DC voltage. Now, I don't want to use this voltage because the magnitude of this voltage, it is too small. We can go and introduce what we call a voltage bias. Now, with the voltage bias, again, it is very important. How is this voltage biased? Now, if I go and use a voltage bias, then I will go and say, with this circuit, let me introduce a bias. Now, with this bias, it simply means that now I am increasing the magnitude of my DC voltage. I am increasing the magnitude of my DC voltage. Now, with the magnitude being increased of the DC voltage, if I connect this in this manner, then I will say the bias, it is connected in this manner. Then I say this bias, I am saying it is 4 volts. This bias, it is 4 volts. Now, if I look at the magnitude at which I am switching on, you will see that this is positive, negative. This is positive, negative, positive, negative. Then with this voltage on the output, for me to be able to switch on this diode, so that I can get the characteristics, I must also match up this bias voltage. You will see that it's a 4 volt bias, switching on 0.3. Now, how is the input? The input is what? The input is 10 volts P, which means this diode can be able to be switched on. Then I will go and say the output that will exist when the bias is introduced, your V out, it will be a V out of your V bias plus 0.7 volts. Sorry, not 0.7, mistake. 0.3 volts. Your V bias, it will be, so your output voltage, it will be your V bias plus 0.3 volt, which means now I have got a V bias of 4 volts plus 0.3, which will give me 4.3 volts, which means when the output is measured, when the output is when the output is measured based on your graphical analysis of these. Your graphical analysis of these, you will see that during switching on up until this voltage is measured, it's going to be 0,3 plus 4 volts, which will be 4,3. Then that is where your output will be. That is where your output will be, which means during the bias introduced, then you will have a 4,3 volt. 4,3 volt. That is going to exist at the output. I have clicked off anything that I don't want to use with respect to this condition here, which is what? From 4,3 all the way up until 10 volts. It was not necessary for my circuit. The only part that I wanted to use was from 0 up until 4,3 volts. Then during the off state, I also needed that portion there. Now, that is a condition that exists within a clamper circuit. That is a condition that exists within a clamper circuit. But now, what will happen? Ali, can you screenshot this?
Okay. You can continue.
Now, what will happen when now I am biasing this, but now with the polarity of this changed? I am biasing this with the polarity of this changed. If I change the polarity of this, then I say that is, let me just use a different color. This time green. I'm changing this. Then I say this one there, that one there. Negative, positive. Now, if I change this in this manner, then I will have introduced a bias. But now, how is going to be the response of the circuit with respect to that bias there? How is going to be the response of the circuit with respect to that bias there? You will see that now when I look at this as an output, I'm going to look at an energizer. Remember, we are energizing from the positive cycle. Don't forget, we are energizing from the positive cycle. The negative cycle switches on, so switches off, then the positive cycle switches on. But now, what will happen to the output during the process where I am energizing with the positive cycle? Then when I measure here, I need to measure an output voltage. Which means now, at this point, my V out will be a V out of positive, negative, negative, positive, which means it is going to be your 0,3 minus V bias. I hope you can spot the difference. It's going to be 0,3 minus V bias, which means here it will be 0,3 minus 4, which is minus 3,7 volts. Minus 3,7 volts. Now, if you look at the state at which this output is, you will see that with this value, during the positive cycle, what did it do? It went and said, previously, I need to cut off, I need to cut off what I don't want to use. I didn't want to use anything above 4,3. I didn't want to use anything above 0,3 previously. But now, when I introduce a bias in this way, it simply means that I don't want to use anything above what I see there. But now, if you look at the position at which this voltage is, you will see that that voltage it is at minus 7,3. What is minus 7,3? If you look at the magnitude here, you will see the magnitude here is 0, positive going that side, negative going that side. But that output is on the negative side, which means it needs to be somewhere there. It needs to be somewhere there, which is my minus 3,7 volt, which means anything that is above that voltage, it is not something that I wanted to use, because it says you can only use a V out of minus 3,7, minus 3,7, minus 3,7 and below, which means on your signal, it is going to cut that signal in that manner. Anything above that side, it is not useful to this circuit. Anything below that, it is useful to that circuit. That's why now you will find your signal, it is in this manner. Now you will find your signal, it is in that manner. Now it simply means that whatever that I see at the output, it must be according to how I want my output to be. I don't want anything above, but I want anything that is below my 3,7 volts. Then I will cut from 10 to 0 up until I get to minus 3,7. Then I will continue with my signal as it is. That is another way of biasing this. Now, with these three states that I've mentioned, that is how you do a positive limiter or positive clipper circuit. Screenshot this only.
Okay, and can we stop the recording for the next part?
Okay.
Not yet. Are you done or not yet?
No. For this part, you can stop the recording and then we can just give it 5 minutes, then we can continue again.
Okay.
Did you screenshot this one?
Yes, I did.
Screenshot, give it 5 minutes, then we start recording again.
Okay.